So there are different types of solutions. A solution can be any combination of phases, solid, liquid, gas. Very common is an aqueous solution where water is the solvent. The solute can be a gas, a liquid, or a solid. And so here in this table from your textbook, we have several examples of solutions. The air in this classroom is a solution of gases. It's a homogeneous mixture of gases. Many metals are not pure metals. They're alloys. I've got a wedding ring, and it was gold, but it's not pure gold. Pure gold doesn't make very good rings because it's too soft. So the gold is mixed with other elements, other metals, to make an alloy that has better properties. And an alloy is a mixture of two different metals, two or more different metals. Of course, you take a chunk of iron and a chunk of lead, and you can't just mix them together, right? You melt them first. You make them into a liquid, then you mix them together, and when you let them cool, they form an alloy. So there's no solvent that will dissolve all possible solutes, which is probably a good thing, because if that got out of control, the whole universe might dissolve. Who knows? So we talk about the solubility of a substance. That's the amount of that substance that will dissolve in a given amount of solvent. Solubility is going to depend on that tendency towards mixing, and also depend on the types of intermolecular forces that are present between the solute and the solvent. Here we have an illustration of probably like club soda, where we have carbon dioxide gas that's dissolved in water. We've talked a lot about energy and how many things happen because it reduces the potential energy of the system. Formation of a solution doesn't necessarily change the potential energy of the particles in that system. If we look at this example here, we have a box where we have neon gas and argon gas, and those two gases are separated by a divider, kind of like the water example. If we remove the divider, I think just understanding kinetic molecular theory of gases, that the particles move in straight lines until they run into things, we could predict that this is going to happen. The gases are going to mix. Does that lower the potential energy of the gases? No. It doesn't change their potential energy at all. They're just mixed. So then why do they mix? There must be some reason. And that reason is entropy. So energy has a tendency to disperse, to spread out, or become randomized. And entropy is a measure of energy randomization. So when those two ideal gases mix, each gas has kinetic energy. When they mix, their kinetic energy is spread out or dispersed over a larger volume. So if you go back and look at this, here the kinetic energy of neon atoms is limited to this part of the box. After they've mixed, the kinetic energy of the neon atoms are spread out over a larger volume. It's the same kinetic energy, but they're spread out. And that has to do with entropy. The argon also was limited to this area, and now the energy has spread out. We see evidence of entropy in all sorts of everyday things. Okay, so it's fall, and the leaves are falling. Do they fall into neat piles? No. They fall into big jumbled messes, right? And the wind blows them around and they get everywhere. They were quite ordered on the tree. Each branch has its leaves in a certain way, depending on the type of tree. When they fall off, all of that order is lost. Everything has potential energy. When it has kinetic energy too. When those leaves fall and get spread out, And randomized, that's a dispersal of their energy. It's an increase in entropy. Have you ever played 52 card pickup? It's a game where you take the deck of cards and you get some gullible person, hey, you want to play 52 card pickup? And then you flick them and they just go all over the place, right? And they just are all over the floor. Some of them are face up, some are face down, some might stick in the trash can, or you never know. They do not line up in suits by color, right? They don't do that. And we understand that that's a very normal thing, but that again has to do with entropy. My house is a study in entropy. So substances mix because of this tendency for energy to spread out whenever it is not restrained from doing so. This also explains why thermal energy transfers from hot objects to cold objects. Why does it do that? Well, because there's this tendency, entropy, for energy to spread out. And so when the thermal energy moves from the hot object to the cold object, it spreads out, it occupies more space, or occupies a larger volume. You'll learn a lot more about entropy in Chem 1B. This is just like a little introduction to it. The intermolecular forces that are present have a large effect on whether a solution will form or not. Here we have an illustration of several different types of intermolecular forces. So here we have heptane and pentane. These are both alkanes, just carbon and hydrogen. All of their bonds are nonpolar. The compounds are nonpolar. So the only thing that's going to attract these two molecules to each other are dispersion forces. Everything has dispersion forces. Here we have two polar molecules, and these will be attracted through dipole-dipole forces. They also have dispersion forces. And then we have, here's ethanol and water. These are polar molecules. They have dipole-dipole forces and dispersion forces, but they also have hydrogen bonding, which is the attraction between the hydrogen on this molecule and the oxygen on another molecule. It's not covalent bonds, it's not ionic bonds, it's between two different molecules. So if you think of intermolecular forces as being like Velcro on the outside of the molecules. I should have brought my mole. If you think of well, I'll just describe it. I should have brought it with me. So I have this little mole, and he's wearing a lab coat, right? And his lab coat fastens with Velcro. So putting the two sides of the lab coat together with the Velcro is like the intermolecular forces between two molecules. The lab coat itself is held together with stitching, right? There's a front and a back, and there's sleeves and the Velcro and everything, and it's all sewed together. When I take the Velcro apart, I am not changing the coat, right? I don't change the molecule when I break the intermolecular forces. I'm just pulling these two things apart. If I were to break the stitching, then I'd be destroying the lab coat itself. That would be like breaking covalent bonds. So the covalent bonds are holding this molecule together, and in physical changes, those covalent bonds do not change at all. They don't get broken or made. All we're doing is messing around with the Velcro between. Okay? So hydrogen bonding typically is stronger Velcro, and dispersion forces is weaker Velcro. And the larger the molecule, the larger the surface area, the better the Velcro sticks. We also have the ion dipole force, which is between an actual ion, not just a polar molecule, an actual ion with generally water molecules in a solution. So these forces can contribute to the formation of a solution, or they can work against the formation of a solution. So in a solution, we have at least two different kinds of particles. And so we can look at the interactions between those two different particles. We also have to consider the interactions between the solvent molecules and between the solute molecules. In order for a solution to mix, the solute particles need to penetrate into the solvent. If these solvent attractions are really strong, the solute might not be able to get in. Or if the solute interactions are very strong, it might not dissolve and it might just stay together and a solution will not form. So a phrase that we use to help us remember this is like dissolves like. So to predict whether a solution will form, you look at the types of intermolecular forces that are present. If they are similar, then a solution will most likely form. If they are different, a solution will probably not form. We talked about miscible earlier. Miscible describes two liquids that are soluble in each other in all proportions. This is not true of all liquids that are soluble. An example of this, though, is ethanol and water. You could take a cup of ethanol and put a teaspoon of water in it, and it makes up just fine. In that case, ethanol would be the solvent. You could take a cup of water and put a teaspoon of ethanol in it, and it would mix up just fine. Ethanol and water can be mixed in any ratio. They are miscible. So the formation of a solution is going to depend on the strength of these intermolecular forces. So if our solvent-solute interactions are stronger than the interactions between solvent molecules and between solute molecules, a solution will form. Because here we have the solvent and the solute being more attracted to each other than they are to others of their own kind. If the solvent-solute interactions are equal to the solvent-solvent and solute-solute, a solution will form. Because it's not losing anything by mixing. Yeah?
Does interactions
intermolecular forces, yeah. Yeah. Yep. If the solvent-solute interactions are weaker than the interactions of the solvent with itself and the solute with itself, a solution may or may not form. It depends on how big that difference is. Even if you lose some energy breaking stronger interactions to form weaker ones, there's that contribution of entropy that can make up for a loss in energy. So you can have weak solute-solvent interactions and still have a solution, but if they're much weaker, then that gain in entropy won't make up for the loss of energy. So we should be able to make predictions like this. Determine whether each compound is soluble in hexane. So what we want to do is we want to identify, are these polar substances or nonpolar substances? Well, you're not given the formula for hexane, but you should be at least able to identify whether it's polar or nonpolar. Hexane, what does hex mean? 6. Penta means 5. So 6, so we have 6 carbons. That's 5, 6 carbons. And then they each need to have 4 bonds, and so the others will be made up with single bonds with hydrogens. So this molecule only has nonpolar bonds, right? Because carbon and hydrogen are close enough in electronegativity that the carbon-hydrogen bond is considered nonpolar. So that means that hexane is a nonpolar substance. So what kind of intermolecular forces does it have? Just dispersion forces. So here we have water. Is water polar or nonpolar? It's polar. What's the strongest intermolecular force in water? Hydrogen bonding. So, is water like hexane? No. We have polar and nonpolar, right? Like dissolves like. These are not like. These are different. So we would predict, no, this will not be soluble in hexane. How about ammonia? Is ammonia polar? Well, you might not be able to tell just by looking at the formula. You may have to draw a Lewis structure. What does that lone pair on the nitrogen tell you? It's polar. So ammonia is polar. Will it dissolve in hexane? Nope. Here's propane. Just carbons and hydrogens. Is that polar? No, it's nonpolar. So here we've got nonpolar and nonpolar. Will that dissolve? Yeah, it should. So this should be soluble. Like dissolves like. Would ammonia dissolve in water? Probably. They're both polar. So we would predict that they would. And they do. And then we have hydrogen chloride. Is that polar or nonpolar? It's polar. So that's a very simple molecule. There's only one bond. That's a bond between two different elements, so you predict that it's polar.
Are the polarities the only thing we need to look at to find out if it's solid?
For a question like this, generally, yeah, it's just a polarity. I mean, you can go into which exact types of intermolecular forces there are, but generally just polar and polar or nonpolar and nonpolar. So this is polar. Will it dissolve in the nonpolar hexane? No. Any questions? Yeah.
So the bond, you mix it, they don't have a color?
No, when you mix it, it will form a solution.
But I mean, last time we were experiment, and the sense is like colorless when you mix it with water and enough. So it's like.
Yeah, it'll be. Well, I mean, it depends on what color the liquids are. All of these liquids don't have a color. But if you try to mix hexane and water, you'll have two layers, two clear layers, and there'll be a thing in the middle.
You can't see it.
What?
But you can't see it.
Well, you can see it.